Okay, let's get started. So we are going to now continue from where we left off last time and talk about the first real topic in the course, which is distributed systems architecture. Okay, as far as the book is concerned, I believe that is chapter 2 of the book. Okay, chapter 1 was just a quick introduction. So before we start, a reminder that we don't use your laptops or phones or anything in the class because we don't allow it. Okay, so this is our sort of the outline for the class. I'm going to have this lecture in 3 modules or 3 parts. Okay, the first part with each is about 25 minutes. Okay, so that will allow us to pace ourselves well. The first part is going to be a broad brush overview of various architectures. Okay, the second part is going to talk about client server and multi-tier architectures, and the third part is going to talk about peer-to-peer, BitTorrent, and more so emerging architectures of that sort. Okay, so let's get started. So we will go through a few different architectures for designing distributed system. Okay, so any system that you see that's distributed will fall into one of these many categories that we are going to cover today. Okay, so we'll start with a simple one, which is layered design. I briefly talked about this last time when I was talking about OS kernels. If you remember, I said in a layered architecture, in the kernel context, you have a network stack that is designed as a layered architecture. You can design entire systems this way. Okay? So in this case, components of your distributed system or your distributed applications are partitioned into layers. Okay? And layers are stacked. Each layer can communicate with the layer above it or the layer below it. Okay, I'm going to talk in a little bit about multi-tier architecture that essentially follow this layered format. Okay, so one restriction here is if layer I needs to talk to, let's say, layer I plus 2, it cannot do so directly. Okay, because each layer is restricted to only communicating with the layer above and below it. So if it has to communicate with other layers, it has to happen indirectly through intermediate layers until you get to the one you need to talk to. Okay? So that's layer design. Now, because layer design is somewhat restrictive in prohibiting components from talking to layers other than the one below and above it, you can generalize this. Okay, and just have a more general architecture, which is called object-oriented architecture, which if you've written Java or used any object-oriented programming language, you know what objects are. Okay? Now, in a distributed system, each object could actually reside on a different machine. Okay? And objects are still communicating with one another. Okay, as you can see with as shown by the arrows. Okay. Now in this case, for the purposes of this lecture, it doesn't matter where the objects reside. What matters is what the architecture is. Okay. The architecture essentially says take your system or your application, partition it into objects. Okay. And then objects will expose an interface, and you can essentially invoke a method or a interface call that is basically exposed by any other object. So any object in this case can communicate with any other object through the published interface for that object. Okay? Very similar to what happens in let's say an object-oriented program that you write, except that this is a distributed application or a distributed system and the objects themselves are distributed. Okay? So we relaxed a restriction on the layered architecture. Here any object can communicate with any other object. Okay, so more flexible architecture. Yeah, this is popular, as you will see, in many different scenarios, including client-server systems. Okay, the third architecture, which you probably, maybe you have seen instances of the first two, but this one is popular but not that common in sort of simple systems. You use these kinds of architectures for designing more complex distributed systems, and this one is called an event-based architecture. So in this case, you have components. Okay, they could be objects, but we are just going to refer to them as components. Your application is partitioned into components. Okay? Components communicate with one another over what is called an event bus. Yeah, the event bus is essentially the layer that enables these components to communicate with one another, and they do so by publishing events or subscribing to events. Okay, that's the method by which they communicate. Okay, they're not necessarily things like RPCs or method calls. They are essentially you publish an event or you subscribe to an event. There's a question in the back. Okay, question is what is an event? So in the context of an event-based architecture, we will leave that as a very general concept. Event could be a data that you publish. Okay, that could be an event. It could, so let's say example could be if you have a weather application. Okay, the events you're publishing are essentially weather updates. Okay, every time you have a new temperature value for a certain city, you will publish that. It's called a new event. Okay, so if you basically don't limit it necessarily to data, but you can assume for simplicity that it could be an update on a data or new data that you want to send to some other component. Okay. Okay. Question is, are interrupts an event? So as I said, this is a very general concept. Events could be interrupts, exceptions. They could be actual data. They could be other kinds of things that you want to use for communication. So the architecture does not limit you. Okay, but what it does is whatever you want to communicate with, you use the event abstraction to do so. Okay, events could be very simply data, but there could be anything else that you want to send to some other component. Okay, but the important part that that I'm trying to emphasize here is components are not directly communicating with other components. They are doing so via the event bus. Okay, you are going to publish your event to the event bus. Other components are going to subscribe to certain kinds of events. The event bus is going to do a matching, saying this component has subscribed to all events of type such and such. Here is a new update, so let's deliver it to them. Okay, so that's basically how communication is going to happen. You are not going to have component I directly send a message to component J, for example. Okay, yes, question there?
Does the event bus is like a queue or something where it has memory and then you keep pushing the events and then it will keep delivering? Is it like that?
Okay.
Like
so question is, what is the event bus? Is it a queue that's going to buffer data and deliver it and so on? Okay, so the answer to that question actually depends on what kind of an event-based architecture that is. This is a very abstract picture. It doesn't actually show what type of an event bus it is. We will actually encounter many different kinds of event buses. In some cases, they could be in-memory queues. In other cases, there will be disk-based queues where the events are actually stored on disk and can be delivered at some later time. Okay, so we also not said when the events are delivered. This is an asynchronous model. You can have immediate delivery, you can have things that are stored and delivered at later time. All of those fall under this category. Okay? What is important is to understand the concept of an event and how the communication actually takes place. Okay? This kind of architecture is also referred to as a publish-subscribe architecture or a pub-sub architecture. Okay? So in most of the pub-sub architecture, you are publishing events, okay, or data is a type of event, and you are subscribing to types of events. And whenever an event of interest is actually published by a publisher, you will get it from the event bus. Okay? It will be delivered to you from the event bus. Okay, is that clear? Okay, it's called event-based. There's a related architecture here which is called the shared data space architecture. This also looks like an event-based architecture, but it's a little different from what I showed you on the previous slide. Okay? It's also called the bulletin board architecture. Okay? So in this case, again, you have your applications partitioned into components. Okay? Application components can actually publish events or data, but they are actually going to put it into the shared persistent data space, which is what we'll call also bulletin board. Okay. Now other components can come at some later point in time and take delivery of whatever is put on the event on the bulletin board. Okay, so this is like think of it as a physical bulletin board where, let's say, you want to sell some furniture that you want to get rid of. You make a note, you go put up a notice on the bulletin board. It's not addressed to anyone in specific. It's just an announcement saying, I want to sell furniture. Okay? And then maybe someone else comes along, looks for notices of interest, and if they find some match, they're going to basically contact you. Okay? The same is true here. Okay? So in this case, what I just said is whatever data or events you're publishing is not addressed to any component in particular. Okay? You're just publishing some information saying this is some information. and you just put it there, and later on some other components can come along and keep looking for that information of interest, and if so, consume it. Okay, yes, question there.
So the main difference here is the components need to do the searching rather than get that stuff forced to them.
Okay, that's a good question. The question is, do the components have to search, or can they be actually push data? So how the data that's published to the bulletin board is sent to the component is flexible. You can have both the push or the pull model. Okay, if the components are looking for it, is the pull model. They're pulling information. If you register your interest to the bulletin board saying, anytime somebody posts a notice about furniture for sale, tell me, or a used car, tell me, that's a push model. Both are possible. Okay. The interesting thing that is different from the event-based architecture is this is decoupled in time. Okay. In the previous event-based architecture, this is somewhat real-time. Events that are published are more or less immediately sent to subscribers. Here, they may sit on the bulletin board for long periods of time. Just as you put a notice, it will sit there for maybe weeks until you take it off. So this is a difference, which is why it says it's decoupled in space and time. Okay. We will come back to the bulletin board architecture towards the very end of the course when we look at middleware system, because these also are a form of middleware. Okay. Any questions about the bulletin board or the event-based architecture? Okay. So yet another architecture, and one that has become very popular, is called a REST architecture, a resource-based architecture. Okay? So a common example of a resource-based architecture is what is called the representational state transfer, or a RESTful architecture. Okay? Practically most modern web services that you encounter today are RESTful. Okay, what does RESTful mean? RESTful services essentially mean they have these 4 characteristics that are listed here, which is that all resources, okay, which could be methods, data, are essentially accessed using a standard naming scheme, okay, or a standard interface. All services that are RESTful essentially offer that interface, and we will see that in the context of web services, you are going to use HTTP naming to offer that interface. Okay, but HTTP is just one example of how to build a RESTful service. It doesn't have to be HTTP based. Okay. Messages are going to be fully described, which means all the information that you need is essentially part of the name. Okay, and essentially the service is stateless, which means it's not going to keep state of the caller once the service actually has executed the request. Okay. Now those are the characteristics of this. We will encounter RESTful services. If some of the lab assignments that we will actually build will actually require you to implement RESTful services. So by the end of this class, you will be very familiar with what these are, because this is how many web-based services are built. But here's a very simple example. Yeah, actually 2 different examples. One is how to make requests. Okay, so if you're going to use HTTP to build your application. So what this means is application components are communicating using HTTP requests. Okay, you must have encountered browsers talking to servers. Okay, you have your browser, you make a HTTP request, it basically contacts a web server, gets some content. Okay, that's just one way how web applications work. You can actually write distributed applications that communicate using HTTP. They are not exchanging web pages. Okay, they're actually exchanging requests and responses, but they're basically using HTTP to make a request and get a response. Okay, and you can use the method to make any request and get any response, not necessarily fetch web content like HTML. This is just a standard way by which you can make a request and get a response. Okay, so that's how RESTful web services are built, and we will also see later on in the course that all of these HTTP operations are of one of 4 types. You can make a GET request, a PUT request, a DELETE request, or a POST request. Those are the types of requests that HTTP supports. Any standard HTTP supports. Okay, and you will write your RESTful web service also using those 4 requests. Okay. So here's a very simple example of an RESTful web service, and I'm going to use Amazon's cloud service for their storage service. Okay, there's something called Simple Storage Service, or S3. Okay, so S3 uses a RESTful interface like most web services, and so S3 is essentially a storage service that allows you to store some data in your cloud. Okay? The way you are going to go access that data is you are going to send an HTTP request, requesting it, and it's going to look like this. So there's going to be a name for the bucket that you have put your data in. It'll say s3.aws.com, and there'll be an object name. Okay? And you will put a get in front of it saying get the object that is essentially mentioned in this URL. Yes, your question there.
Is Apache Kafka exclusive to the PubSub architecture?
Can you repeat your question?
Is Apache Kafka exclusive to the PubSub architecture?
So question is Apache Kafka, does it use the PubSub
Or
architecture?
is it like also you use both people?
Right, so Kafka is, for those of you who may not be familiar with it, it's an Apache project that's used to build distributed applications. Kafka uses PubSub internal. Okay. Now, most of these don't actually say this is purely PubSub or purely event-based. Many of them support many different flavors of what you can do with it. Okay. We might encounter Kafka later on in the course when I start doing some case studies of this middleware system. Kafka is actually an example of middleware that you will use to write distributed applications. Okay. It does, like many other systems, also support PubSub. Okay. But coming back to RESTful architectures, okay, so this is how you are going to make requests. Okay. So have an HTTP URL, okay, and the URL is essentially includes as whatever you are trying to get from the server. Okay. It might actually include a long URL, might actually include all sorts of other information that tells the server what are you looking for. Okay. Google Maps will use a RESTful interface, and you can actually have the location that you want as part of the URL, so it knows what you want. Okay. So that's a quick example. We'll come back to this. This is just for you to understand what RESTful web services look like. So that's how you make a request, and typically the way you are going to get a response for that request, the server is going to process it and send you a response. Okay, there are many ways to send the response as well. Okay. A common way is to construct what's called a JSON object and send that object back. Okay. JSON is essentially JavaScript object notation. Yeah, or object naming, maybe, I can't remember. But this is basically a way you can actually send a response back which is self-descriptive. So let's say you send a request for some information, you will essentially get a response that might look like this, which is all textual, but there are tuples saying name is this, the message that I want to send from that name is this, which are set of strings, and then maybe there are some attributes saying age is this and so on. Okay, so there are pairwise attributes where you say this is the key, that's the value. Okay, so key colon value, and you will essentially have a list of these in your response. So this is how you are going to actually take any response that you want to send and send it back. So now this is not what's going to come back if you request an S3 object. You might actually get some data from that object also as an object. Okay. Any questions on this? Okay, so we'll come back to all of these in more detail. This is just a high-level introduction as to what architectures you can use. Okay, so that's essentially the first module where we just went through 5 different architectures. Okay, I'm going to take a pause here. We'll switch to second module for the lecture, which is going to be client-server architectures and multi-tier architectures. Any questions about event-based, Blackboard architecture, RESTful web services, and so on? Yes.
So what do you mean when you say decoupled in space?
Okay, so question is, what do you mean by when you say decoupled? In fact, that slide essentially said the architecture is decoupled in space and time. Okay, so time essentially means you can make a request or publish an event at one point, it will get delivered at some arbitrary later time. It's not real time where you send the request, get a response. That's what time is. Space essentially means you don't address your request to anyone in particular. Okay. If you are doing, let's say, socket-based communication, you are communicating with the IP address. So all the packets are actually addressed to some specific machine. Here, because you are saying, I want to sell furniture, okay, you are not sending that message to any one per person or an object, you're just putting up that message. Okay? So that's what space means. In most cases, when you communicate, you have an intended recipient for the communication. The message is actually addressed to that component or an endpoint. Okay? In this architecture, messages are not addressed to anyone, which is why it's decoupled in space. Yes, question there.
Is there an example of this state data space, some common application that
Okay, is there an example of shared data space? When we come back to distributed middleware, we are going to look at Genie as an example. That's a Java-based bulletin board architecture. Okay, it was designed for embedded systems. Didn't actually take off. There were some applications built with it, then it kind of fizzled out. But that's an example. There are many others, but that's the one we are going to cover in the course. But later on.
Is this a popular one or is it like just like marginal, like this kind of one?
Okay, so question is it popular or not? So these kinds of architectures are only used in very specific context. You don't want to write a web server or some web service this way. Okay? There's a specific reason you want to use it in this fashion. The other example that I wanted to mention in this context is this is how many systems are being used for configuration. One of the ways you could actually use this is when you enter and when a machine enters a network environment, it allows you to discover what services are there, because every service in that environment has put up a note on the shared data space. So for example, every printer would have said, I am a printer, this is the printer name, this is the printer model. So now if you arrive with a laptop in a new Wi-Fi network, it can auto-discover all the services that are the databases, web services, printers, and so on. So that's another example, but there is no middleware as such. They are built as a one-off way to do this kind of stuff. Yes, question.
The event-based model does the order in which the events are published from the publisher and the events like received by the subscriber. Does it need to be in the same order? Like,
okay. Question is, does the event-based architecture require that the event ordering be maintained, that the event should be delivered in the order in which they are published? Okay. That again depends on the event-based architecture. Most of them will basically do FIFO deliver. That's the default, which means that whatever order you publish in will be the order in which you deliver. But that's not necessarily true every time. There are event-based architecture that allow you to have priorities on events, for example. So higher priority events can get delivered faster. So, because this is a very general thing we are talking. We are not talking about a specific system that does this. This is just a broad concept. So there are many systems that have made different assumptions. Okay, so there is no one answer to that question. But by and large, yes, delivery is in order of in which they are published. Okay. Okay. So moving on to the second part. Okay, so we'll now talk about the client-server architecture, because this is also the most popular one. Okay, and you should at least have heard of the term. Okay, in the client-server architecture, there are at least two machines: a client machine that is making requests, and a server machine that's answering requests. The server is providing some service; it answers requests. Okay, and here's a very simple example of how a client-server interaction occurs. The x-axis here is time. Okay, this is a timeline figure. Okay, and so anything that is bold says that that entity is actually executing something. If it's dotted, it means it's waiting. Okay, so initially the client is executing on a client machine. It sends a request. Okay, and then it waits, which is why there's a dotted line. The request traverses a network, arrives at the server. The server then processes the request, which is why there is bold here. Okay, and then a response goes back to the client, and then the client resumes execution. Very standard approach for building any client-server architecture. Okay. Now, in this very simple example, it appears that the server is actually one entity. Okay, so the system is distributed because there is at least one client and at least one server. Typically, there will be many clients and a server. Okay? But in a very complex application, that server that we see there is not one entity. It could be a collection of servers that are providing that service. Okay? So what we have labeled here as server actually could be more than one server that are collectively doing this, and that is what we want to look at in more detail through what is called multi-tier architectures. The servers will actually be organized in tiers, and we'll see how they actually process requests. Okay? But to understand why you actually need to have more than one server to do more than one task, we should think about what the distributed application is actually trying to do. Okay? So if you think of any abstract application, it will have several common functions. Okay? There will be some sort of a user interface that the user is using to interact with the application. Okay? So that's the user interface layer. Okay? There's some processing that the application will do when the user makes request. You have to process that request. Okay? That's the processing layer. Okay? And maybe the request access some data. Okay? Data could be a file, it could be some data in a database. What the data is, it doesn't matter. But the request might often access some data in order to provide a response. Okay? So the application is actually going to store some data as part of its overall code, and that's the data layer. Okay? So most distributed application, even centralized applications for that matter, will have an interface that they use to interact with the user. There's some processing, and then there is some data that they manage. Yes, the same is true in the case of a distributed application, but then here is an example that makes that a little more explicit. Okay? This example shows you a search engine. Okay? In fact, it's an abstract representation of a search engine because real search engines are massively distributed. Okay? They run on hundreds of thousands of machines. Okay? But for the purposes of this example, that doesn't matter. We are just trying to understand what components does the search engine have. Okay? And you will see those three things that I mentioned. Okay? There are, at the top is the end user interface, okay? Which is very simple. That's a search box typically in a browser. Okay? So that part is very straightforward in this case. Okay? But the processing layer is fairly complicated. Okay? There may be lots of things happening. Okay? So for example, there is web crawling, which is not even shown here, where that component goes and actually downloads web pages and indexes them. Okay? So that's actually not shown here. But assuming you have done the crawling and you created a repository of all the web pages you crawled and indexed them, all of that data is going to be stored in the data layer. Okay, so that's essentially all the data you crawled, all the web page content and an index. Okay. Now your interface, when the user types some keywords, is going to generate a query to the search engine. Okay, so you'll send these text phrases off to the search engine. The search engine will have a query generator that's going to internally make a query. Okay, that is where the request is getting processed. The query is going to be sent off to your database, which is essentially your index. Okay, you are going to get the results of all the matches, okay, and then you're going to have some sort of a ranking algorithm that says of all the results, which one, let's order them by some rank or relevance. Okay. So then you're going to process those results, reorder them, okay, then you're going to take all those results and make an HTML page out of it, okay, and that HTML page is going to be sent back to the user. Okay, you don't need to know what search engines do. It's just an example that shows you how the requests arrive, how it's processed, and how a response is generated. Okay, so what is important to understand is we have a data layer, okay, which is where in this case all the web pages are indexed and stored. Okay, it could be a database but doesn't have to be. And this is all the processing. Okay, there are many components here. There is the query generator, there's the ranking algorithm, the HTML generator. There will be many more that are not shown here. Okay, so that's a fairly complicated layer. And then you have the user interface, which in this case is straightforward. Okay, so keep this example in mind as we start digging deeper. Okay, any questions on this? Okay, so now we can ask the question as to if you want to build a distributed application that's a search engine, what part, okay, of all of this is going to happen on the client and what part is going to happen on the server. Okay, where do you, so this is just saying the application has three layers, a user interface layer, processing layer and a data layer. Okay. Now you can ask saying, okay, which of this is going to be at the client, which of this is at the server. Now in this case the answer is trivial. You are going to say that everything above, that's a user interface, is at the client, everything else is at the server. Okay? But in many applications that boundary is going to be dependent on what assumptions you make about your system design. Okay? So in addition to these three layers, you have to ask the question, which of these layers actually reside on the server and which of these reside on the client, and this is where things start getting a little more interesting. Okay? So we will assume that clients are not that powerful. Okay, they can do simple processing tasks but not complicated ones. Okay? And the servers are more powerful, they can actually have more than one servers doing the task, so they can do bulk of the work. So that's one assumption that we are going to make. Okay? And what this slide shows is how you can take any application and split it between your client and the server. Okay? So you will see that there is essentially the user interface, the processing layer, which is shown as the application box, and the data layer, which is shown as the database. Okay? So So this dotted line here is the boundary between the client and the server, and this each column here shows you one design choice. It says what did you decide to put on the client and what did you decide to put on the server. Okay, that very simple example that I showed you, the search engine example, okay, is here where the interface, hold on for a second. What seems to be making noises? Okay, so the interface is at the client and the application and the database is at the server. Okay, so this is the boundary between the client and the server, but you will see that there are many choices. In one case, you might have part of the user interface at the server, part of it is at the client, and the part of it is the server. Okay, and then the application and the database is all at the server. Here's another example where your part of the application, actually code is running on the client, the user interface is completely on the client, part of it is on the server, database is completely on the server. Here you actually put the interface and the application on the client, the database is on the server, and here you can split the database. Okay? Now you can ask, can you think of examples of applications you have interacted with that actually fall into this category? Okay, so where would you see scenarios where some user interface processing is happening on the client and some of it is happening on the server? Okay, so if you have JavaScript applications, okay, the browser is going to run JavaScript code. Okay, some of it is going to be done on the client. Okay, and then when you actually make requests, some more processing will actually happen on the server. Okay, and then all the rest also happens on the server. Okay. What about this scenario where the user interface part of the application is on the client, part of it is on the server, and the database is on the server? Google search will be here because you just have a search box, so there's not much application on the client side.
Multiplayer games.
Sorry?
Multiplayer online.
Multiplayer games, you had something? Okay, mobile apps, good example. Okay, if you take any phone app, okay, you have your interface, but the app also runs some code. Typically, the app will also talk to a server where there will be more code, and then there will be some data you may have stored on the cloud. Okay, games is another example. Okay, you might have the interface, but there may be some game client. There is also some game server somewhere else. Okay? So if you start thinking about it, you will understand that these are just different choices, and depending on what application you are trying to build, it will naturally tell you what you want to put on the client, what you want to put on the server. And you can, so these are typical desktop clients where you might actually have a PC based application where the application is completely here and it is just talking to a remote database. That's all it's doing. So the database is actually in the server. You might have this scenario where part of the database is cached on the client for performance reason or distributed or something like that. Okay? So you will get all of these different choices. So when you build an application, a distributed application, you have to decide what do you want to put where. Okay, because there's no apparent one answer that says I'm only going to put this functionality on one place and the other functionality on the other. Okay, the answer is going to be it depends. What is the application? What is it doing? Okay, what performance do I want to see for my users? Okay, anything you put on the server, you got to realize there is going to be a network hop to go to the server and come back. So there's network latency involved. But the server has more resources, right? Because if you're doing something on the phone, if you put too much processing on the phone, the battery life is going to go down. If you put too little, performance will suffer because everything has to go to the server. So it's always going to be a set of trade-offs. You have to pick and choose what makes sense. Is that clear? Okay. So now, even after you make this division between the client and the server, because there's a lot of functionality at the server, you typically will end up using more than one server to perform those tasks. Okay, this is where we start getting into multi-tier application. Okay, so in a multi-tier application, what happens is your server is not one machine, it is a sequence or tier of machines. Okay, there is a tier and request processing is tier based. Okay, and I'm going to come back to this example in just 1 second. I'm going to draw a picture here to show you an example. Okay. Let's say this is your browser. Okay. It's going to make, and let's say you are making a request to some online store. And this is typical architecture of your online store is going to look like this. Okay, so a typical web application will have what are called 3 tiers. Okay, an HTTP tier, an application tier, and a database tier. Okay, the web browser makes a request; it comes to your HTTP server at the on the server side. Okay, that request will then be sent from the HTTP server to an application server, which is where the code for whatever application you are accessing is written. Okay, this is where you might write it in Python or Node.js or whatever your favorite web-based programming language is. Okay, Java, the language doesn't matter. The point is this is where the actual code for that application is going to reside, and then there is a database here, which is where the data for the application is going to reside. Okay? So requests are going to arrive from the browser. They're going to actually go. So this is the first tier. They're going to essentially go from the first tier to the second tier to the third tier, okay? And then responses are going to flow back. Okay, so if you make a simple request to, let's say, an online web store, maybe you are just searching a catalog for a product. Okay, so you basically say, I want to search for a distributed systems textbook. Okay, that request is going to come to the HTTP server. Okay, from there it will come to the web server. The web server will take that request. It will make a database query saying, what books do I have in my catalog that match the terms distributed system. So you'll send that to the database. The database will query the product catalog, send back some responses. Right? They'll come back to the application server. The application server might decide how it wants to present all of those responses, maybe order it or do whatever it needs to do, construct an HTML page out of it. Okay. Send that to the HTTP server, which makes a response to that HTTP request, sends it back to the browser. Okay. So that's how typical web-based applications are going to process requests. Okay? So requests are going to trickle from one tier to another. Okay? Responses are going to go back this way. Okay? In more advanced systems, you might have caches at different tiers, which might basically take previous responses and just return them immediately for performance reasons. At this point, we are not going to assume any caches. Okay? Now, what you will see as because of what we just drawn here, you will see that this maps to the layered architecture that I just showed on the very first slide. Okay? Tiers are essentially layers because each tier only talks to the tier before and after it. Okay? And you may have more than 3, but 3 is the typical way you build these web-based applications, okay? Which is also shown in this case in essentially a time diagram where you make a request, it comes to the application server. Actually, it will come to the HTTP server, which I drew there but not shown in the figure. So the HTTP server will send it to the application server, which will send it to a database server. The responses are going to trickle back. Okay, this is a very standard way to build a web application in a multi-tier fashion. This is how most of these stores are built as well. Yes, question?
In this case, is HTTP server used to hide the rest of your layers of your server, or I mean, what the primary purpose of HTTP server in this case?
Okay, question is what is the primary purpose of the HTTP server? Because this is a web-based application, okay, your browser is going to make HTTP requests. Okay, so there has to be something that answers that HTTP request. So you can build an HTTP server. In many cases, your web application framework might provide HTTP functionality itself. In that case, this is actually, these two things are one and the same thing. Okay, because they can do HTTP processing as well as do code processing the request. But often you might have an Apache web server sitting here. Okay, with just only HTTP processing, nothing more. The Apache web server is simply going to hand your request to whatever you wrote your application in. If you wrote it in Python, your Python code is going to be sitting here and is going to get requests from the HTTP server and process it. Okay. Any other questions? Yes.
So is it always that we should wait for the result from the server? Because if we play online games, maybe the game is still going on, but the responses from later.
Okay, question is, do you always have to wait for the server to return a result? Okay, the answer to that depends on the mode of communication. This is called synchronous or blocking communication. In synchronous or blocking communication, if you make a request, you have to block for the response. Okay, the example you are just asking about, which is gaming, may use asynchronous communication, where you might send a request, okay, but the client does not block, it might start doing other things and is waiting for a response to come asynchronously at a later time. Okay, we will talk about asynchronous servers as well, okay, but not today. Yes, question.
Treat the application server as a black box, then what is the protocol that people usually use to communicate between the HTTP application server?
Okay, question is, what is the protocol used to talk between the HTTP server and the application server? That is based on the application. So you are going to get an HTTP request. Okay? That HTTP request could be used, if it's a RESTful service, it just looks like a big URL. Okay? You might just hand that to the app server saying, here a request has come. There's going to be a connector between the HTTP server and the app server. There's no standard protocol there. This is just a way for the HTTP server to simply invoke code and hand the request to the app server, and the app server will take that request and do whatever it needs to do with it. Okay? So here we are basically using HTTP for communication. All of this communication can be arbitrary. There is no standard for it. From here to here, you are actually sending SQL queries. You might also you might have other kinds of databases like MongoDB that are not even SQL based. Okay, so there is no standard of what protocols are used between here and here. So only thing that standardized is the HTTP layer here. Okay, any other questions? Yes.
And sometimes skip some pairs. I mean,
Can you skip some tier? Is that your question?
Skip some tier. Like HTTP directly connect to the database while application there.
Okay, so typically in this architecture, you don't skip any tiers. Request processing is actually going to proceed forward and responses flow backwards. The only thing you can skip is if you put a cache here, okay, where your cache previous query results, a new query comes and you already made that query, gotten a response, you don't need to make another query. In that case, you will basically, you have your answer, you don't need to proceed further, you will start processing a response. But you will not have HTTP server talking to databases or things like that. This is basically the way the logic is structured for the application. Okay, any questions other than what has been asked on either the multi-tier architecture or the example? I will switch now to the last part, which is peer-to-peer architectures. Okay, so we did multi-tier, and now we are going to do peer-to-peer systems, but all of this broadly falls under the umbrella of decentralized systems. Okay, so in a peer-to-peer architecture, okay, we basically have removed the distinction between a client and a server. Okay. In a client-server architecture, which is very common, you have a client which is assumed to have less resources, okay, and it is making requests of a machine that's a server which has more resources. Okay. In a peer-to-peer, all machines are peers. They can make requests, they can answer requests. Okay. Some of them might do both. So they, in some sense, they can take the role of a server, they can take a role of a client, or they can play both roles. Okay. So that's essentially what peer means, because peer essentially removes, is the name, is what we call a node in this architecture, but we don't distinguish between whether it's a client functionality or a server functionality is running there. It may do either or both. Okay, so that's the first thing. The second interesting aspect of peer-to-peer architectures is there is an overlay network that is used by your system for communication. Okay. So in some sense, these peers will organize themselves in some network topology. Okay. That's independent of the underlying physical network topology. Okay. So in this case, the topology you see is a logical ring. Okay. The underlying network is just, in this case, could be just the internet. Okay. Nodes in the internet are not connected in a ring. This is just a logical ring which says node 7 can only talk to node 8 and node 6. So that's basically a ring topology. Okay. So all peer-to-peer architectures will have some overlay topology, and they use that overlay topology to decide who they talk to. Okay, so in this case you see a ring architecture, but there could be any arbitrary topology, which could be tree, graph, structures, or any arbitrary topology you can think of. Okay, but they will construct that topology and use it for communication. Okay, so those are the two characteristics of peer-to-peer architecture. We are going to look at a few different examples, okay, of how peer-to-peer architectures work. Okay, but is there any question about any thing what I just said? Anything about what I just said? Okay, so the figure that is shown here is a very specific peer-to-peer architecture, which is called CORD. Okay. What CORD does is it's essentially a distributed lookup table or a distributed hash table. Okay. The service that CORD provides is you can essentially provide a key, okay, and it will provide you a value. So you're using it as a key value lookup system. Okay. So you can store arbitrary objects in them. Each object will have a key. The value is essentially that object. Okay. So if you want the object, you are going to specify the key, and then the system is going to do a lookup and tell you where the object resides. Okay. The normal way to do this, and objects are now distributed across peers. It's not that all the objects are stored on one machine. Objects are spread across all the machines. Okay. So the normal way to do this would be have one big table which lists all the objects and which machines they are located on. Okay, that's your lookup table. Okay, except that in CORD, that lookup table itself is distributed. There's no centralized table. It's a decentralized architecture. Okay, so there's no one machine that knows where all the objects are stored. Okay, each of them only has partial information. Okay, so when you make a key value, when you send a request to look up a certain key K, okay, you don't know who actually even knows where that has the entry for that table. Okay, and the object itself may be stored somewhere else. It doesn't even have to be stored where the entry for the table is stored. Okay, so what you will have to do is you will have to inject this query into the network. Okay, the query will have to hop from node to node until it arrives at the node that has the answer you are seeking, which is what is the value corresponding to the key. Okay, which in this case will simply tell you the object resides on this machine. Okay, so what I have just described to you is what is called a distributed hash table. You probably know what a hash table is. A hash table just allows you to give a key, and it basically hashes to a value. That's the value. Okay. In this case, the hash table is distributed, which means that you take that table and you basically distribute it across machine. Okay. Now what CORD does is it has an interesting randomized way by which it actually distributes the hash table responsibility across the peers. Okay. And so that is where all this interesting stuff comes in. So what happens in what CORD assumes is it assumes that all objects that you could ever possibly store in the system, let's say, are going to be numbered from 0 through n. Okay, pick any n. If you have a million objects, you'll have 0 to million or some large number. Okay, so you'll essentially have a range for all the keys that you have in your system. Okay, and then you are going to partition that range and assign responsibility for answering queries for that range to nodes in your system. Okay, and so that's how you are going to do the distribution. That's done in a randomized fashion. So when a peer essentially joins the network, it's going to pick an arbitrary ID for itself, and it's going to join the ring at some point in this ring. Okay, so in this case, let's say you have an example that where the keys go from 0 to 15. Okay, so there are 16 objects in this hash table, or could have 16 objects in this hash table. So when a node, which is a machine, joins, it has to pick an ID for itself that goes from 0 to 15, which has not been chosen before. Okay, and you will join the network at that point. So here a node has joined as ID 7. Okay, that's the node ID. Okay, so here a node has joined. All the dark circles are actual machines. Okay, so that's a node 12, there's node 15, node 4, and so on. Okay, so now if you join a network at a certain point in your logical ring, what that also tells you is that that node is responsible for answering all queries for objects, keys that are basically going in the ring from the previous node until itself. So this node, or the other way around, from this node to the next node. Okay, so here you have this node essentially answering 5, 6, 7. Okay, this node says it's going to answer everything from 8 to 12. Okay, because it joined there, it's going to take responsibility for all keys from the previous node until its own ID. Okay? Is that clear? What I just said? So when you inject an object in or a query request rather into this network, it's going to hop from node to node until it reaches a node that actually has an answer. So if you say I want to look up key 10 and you inject that query there, it's going to be routed through your network, your overlay network, until it arrives here, because 12 is the node that can answer for object number 10.
It has to go through 147 and
Okay, so question is, does it actually go linear? No, there's better query routing than linear search. Okay, but I won't go into how you can actually go logarithmic and so on. But we will not go into query routing. I'm simply explaining how this system actually implements a distributed hash table. Question?
Will we cover this later, or this won't be covered later?
Uh,
The routing, or like how do we manage because I'm assuming that every node has a limited capacity, and what happens when we delete it.
Right. So basically, the readings for the lecture actually has the CORD paper. It's a fairly detailed paper. I'm not going to go into details of CORD because I'm going to also show several other architectures that are also equally interesting. So we can't go into all of them. But yes, some of the query routing details are in there. Okay, this just shows you how you take responsibility and so on. Yes, question there?
What happens if the node leaves the network? What happens to its key?
Okay, that's a good question. So so question is, what happens if a node leaves the network? I hadn't even gotten to that point, but let me answer that question. So what is assumed in a peer-to-peer system is that there can be dynamics in the system, okay? Which means peers can come and go. Unlike a server system, it's not that your database server is gone and then it's going to come back at a later time. Once you start the servers up, it's assumed that the servers remain until they fail or they're shut down. Okay. In a peer-to-peer network, that's not the case. Okay, it's not that the peers, once they join the network, are going to stay there for long periods of time. They may, but you don't assume that they will. They're free to leave the network at any time. Okay. That means every peer-to-peer network needs to take care of dynamic joins and dynamic leaves. Okay. So what that says is, let's say new node joins the network and decides to do, say I'm node 10. So it's going to join the network here. So what that does is the responsibilities for 12 now get split. Okay? 10 is now going to take over answering for 8, 9 and 10 by itself based on our rule, and 12 is only going to answer for objects 11 and 12. Okay, so your distributed hash table has gotten split at 12. Okay? And similarly, if some node leaves, let's say 7 leaves, okay, then the next node in the ring will have to take over its responsibility. Okay, that's the general rule, that if a node leaves, then you have to take over your neighbor's responsibility. If a new node joins as your neighbor, you take some of your work and give it to your neighbor. So you split the work between yourself and the neighbor. Okay? Now you can ask, how does that happen? Okay? Are you going to keep, because if you are the only one who actually has the data and you leave, then the data is lost. So obviously you can't have that happen. You have to have some replication. Although you are responsible for answering those queries, doesn't mean there's only one copy of those key value entries. There has to be some replication that allows you to how to recover from them. Okay? Now there are many peer-to-peer systems that will use different types of replication, different types of techniques that allow you to deal with joins and leaves and so on. Okay, but the basic idea is you need redundancy, and you need to figure out when there are changes in your network, when some node has joined, when some node has left, and what does that do to what your responsibilities are. Will they change or not change? Okay, is there a question, follow-up question you had?
If only a successor takes in the data from a node that is done, that create a load balancing issue?
Question is, if the successor takes over the responsibility, does that not cause a load balancing issue? Yes, I mean, because this is fully randomized, there is no guarantee where nodes are joining, which nodes leave. Okay, so you will see exactly, your question was, will that not cause a load balancing issue? Even in this network, you will see that 1 is only answering requests for 0 and 1. 12 is answering requests for 5 objects. It has 2.5 times the load of 1. That's just an artifact of the fact there is a randomized network. Over long periods of time, things will be stable, but at any one time, there may be skews in what loads peers will see. Okay, that's an artifact of the randomized nature of your system. If you did not want that, you would have to design your system some other way. Saying if there are 100 objects on 4 nodes, each node takes 25 objects. That would be load balanced, but that's not randomized. Okay? Yes.
So where exactly is the data? Is it like placed somewhere and these machines are responsible to pick up those specific amounts of everyone is like given certain data relations or something?
Okay. Question is, where is the data stored, if I'm understanding your question. Okay. So what I showed you here is simply a big lookup table. Okay. It doesn't tell you where the data is stored. Data itself could be stored on these nodes. Okay. They could be replicated. The lookup table is simply telling you which node has this object. Okay. Just because I can answer that question doesn't mean I have it. Okay, I just know that which node has it. So the relationship between where the key value entries are stored and where the objects are stored is actually not direct. Okay? You can have 10 copies of the object. So if you say where is object 10 stored, you will say it's stored in 10 different places. Here are all the nodes. Go pick which node you want and get it from there.
So what are those dotted circles? What do they represent?
Okay, question, what do the dotted circles represent? Each circle represents an object that you could store. Okay, the fact that so there are two things here. There are objects and there are nodes. Okay, so the dark circles represent machines or peers. The dotted circles represent objects, which basically says that this machine is going to answer for requests for all of those objects. Okay, that's all it means. Okay, that's a figure from the book actually. So that's how they chose to draw it. Yes.
And you said that the distributed hash table itself is like distributed among the nodes.
Yes.
So let's say somebody just joins, right? So how does it have information on what's the first point of contact for the node?
Right. Question is, if you join, how do you know who your neighbors are and so on? So there is a join protocol. This is a problem for every peer-to-peer network. Any peer, when they join, they have to pick some neighbors. Okay? If you don't know who is in the network, you're going to say, how am I going to pick neighbors if I don't even know who is in the network? There's a standard bootstrapping protocol. Okay, there has to be a way to bootstrap, saying you have to have some point of entry saying I'm joining, tell me about something, so then you can pick your neighbors, or in this case you will pick a random ID for yourself and your neighbors will have to get discovered and so on. So that's a join protocol for every peer. That's not unique to this system. That's every system has to deal with that. Okay? And so that's part of the join protocol. But I mean, the standard techniques apply. You have to have some well-known place you can go and say I'm going to join, what should I do? Okay? Or you will flood the network in some cases, as you will see. Any other questions? Okay, so I'm going to show a second architecture here. Okay, it is also a peer-to-peer network, but this is a two-dimensional architecture. Okay, if you think about what CORD did, okay, so there was basically one key. Okay, and you basically hash the key, you found the value. Okay. In a two-dimensional architecture, you can assume that every object is represented by two keys, not one key. Okay, you specify both keys to find the value. Okay. That is why there are two dimensions. The keys can vary along independently across two dimensions. Okay. So you can ask, why do I even care? Why should there be 2 or 3 dimensions? Okay. So here's an example. Okay. So let's say in CORD, you had file names as your key. Okay, which is a very simple way to say these are keys. So let's say you have a file called foo, okay, you have a file called bar. So these are your lookup keys. Okay, so you say where is file foo stored? Okay, this will get hashed to some integer internally. Okay, and then it will get routed to some CORD node. It will tell you this such and such machine stores file foo. Okay, so unidimensional keys. Okay. Now what if, why do you need 2 dimensions? You could say I have the file name and the file type. Okay, file type could be this is an image, or this is a video, or this is some other kind of file. Okay, so you could have file foo, that's an image, or file foo, that's a video. Okay, so there are 2 attributes to your file. So you have the file name and the file type that you are trying to access. Okay, so you specify both. So then you do a lookup saying which node has file foo, that's an image, a JPEG image. Or you could say which name has which node rather has file foo, that's a video object. So you specify 2 attributes. Okay, so you're going to do an attribute lookup on 2 attributes. You'll still get a value, except that you have to specify 2 keys in order to do the lookup. Okay? So your peer-to-peer systems that have done 2, you can have n keys. You can think of generalizing this, saying I have n attributes for every object. I specify, I do a query on n attributes, and then I get a value. Okay? So this is basically showing you how you can do this in 2-dimensional space. Okay? So rather than strings and file types, we will just assume the keys are numeric. Okay? They go from 0 to 1 in 2 dimensions. Okay? You can just assume every string can be hashed to an integer, and then you'll basically have a file name that maps to some numeric value, file type that maps into some numeric value. So in this case, each node has to take responsibility for again answering queries that fall in some part of this 2-dimensional space. Okay? So the rectangles essentially to show you the queries that a node which is at the center of that rectangle is responsible for answering. Okay? So this dot here, which is labeled 0.2, 0.3, is the ID of that node, and what that rectangle around it shows is it's actually going to answer for all queries that fall into this part of the X range and that part of the Y range. Okay? And so on and so forth. So whenever a node wants to join, it's going to pick a 2-dimensional coordinate for itself, and it will join the network at that point. That will cause some rectangle to get split. Okay, so here's an example where a node has joined. Okay, so that has caused this rectangle to get split. So now this rectangle is split into 2. The lower node is going to answer only this part of the query space, and the upper node is going to answer that part of the query space. So if you join this rectangle, you'll split that rectangle either vertically or horizontally. It doesn't matter which way. You'll split it and say now the previous node will go to the left half and the new node will go to the right half. So this is how joins are going to occur in this network. Okay. Now when nodes leave, things get more complicated. Okay, because our node might leave, that doesn't allow you to merge rectangles the way you split it. Okay, so for example, if this node here 0.6, 0.7 leaves, okay, you have to assign all of that range to some other rectangle, because there is no one rectangle you can do this. Okay, you might have to actually split it that way and merge it with 2 other rectangles. Okay, so it's not obvious when some node leaves, how do you take its responsibility and repartition it across the network. Joins are easy because you always join a rectangle, you'll split it into 2. That's never a problem. Leaves are not easy because when you leave, whatever was your rectangle has to be joined with someone else. If there isn't another rectangle of the same width or height, you will have to partition your rectangles and rejoin them to others. Okay, so that's a little more complicated. It might involve coordination with multiple peers in order to reassign responsibilities. Okay, so it's a little more complicated network, but effectively it does the same thing. Okay, still a distributed hash table, except that you are hashing on multiple keys. Okay, you have multiple attributes you're hashing on to get to your object. Okay, it lets you do more fine-grained queries than what you had before. Okay, but you can do with either one, doesn't matter really. Any questions on this? Okay, so this is called Content Addressable Network, or CAN. Okay, that's another type of a structured peer-to-peer network that was designed maybe 15 years ago. Yes, question?
So is this like the last peer-to-peer where there's 2 types of nodes, those who answer and those who, like the, because in the last one you had the circle and then,
yes.
Like, and so are you saying that you split rectangles when I guess a special node that answers questions joins the same rectangle, or when any node?
No, so what I showed was when any peer joins the network, it has to join the network somewhere. Just as in the previous case, you joined at some point in a ring. Here you are going to join in some coordinate in this 2-dimensional space. Okay? And because you picked a certain coordinate, you will land in some rectangle already that exists. Okay, then you will have to take the responsibilities of the node that was answering for that rectangle and split that into 2. That's all that I was saying. Okay. Again, there is still a distinction between who can answer queries and who stores the data. That distinction is still there. This is just answering queries. This is just the distributed hash table part of your peer-to-peer network. Data will still be spread across peers that could be replicated, and the hash table has to track which nodes have that data, and when the queries come, you have to return all of that information. Okay. So that part is still true. The only thing that's different here is the queries actually have multiple attributes. In the 2-dimensional space, there are 2 attributes. Okay, there's some question there. Yes.
So you said that a file name and a file type combined becomes a 2D coordinate. That
Yes.
could also be represented as an ID and become a chord system, right? I mean, combinedly a
Yes.
file name and a type. So what's the difference?
So
Why has
yes,
this
so in what you just asked is, in chord I could have simply said this is foo.mp4 or foo.jpeg. They are two different files. Right, so I have basically embedded the file type as a part of my file name. Okay, so yes, I mean there is technically you could take any two keys. I could just concatenate them. It becomes one key.
effectively why did this come?
Right, so the question is basically, do you want a way by which you can do queries that could be more flexible for whatever application you are building? But in terms of expressive power, they are more or less the same. You can take those two keys, because simple thing is if those two keys are strings, I concatenate them, I get one string. That could be my key for the previous case, which is one dimensional. Or vice versa, I could take a one-dimensional key, which is a string, split it into two, now I got two attributes. Okay? So I don't think there is a real difference. It's just a different architecture, but they are actually technically doing the same thing. Okay, yes.
Is the blockchain similar to any of these?
Okay, is the blockchain similar to any of this? So blockchain is a distributed ledger, which is not really a peer-to-peer content-based system. We'll get to blockchains at the very end of the course. Okay, but it's not really a content network. It's not storing content necessarily. It's tracking transactions. Okay, so we'll get to that. Yes.
So in this graph, each key in the real system, will that be just in the file distributed system, or it can also be some different tasks?
Okay, so question is, what does the key represent? Could it be files? Could it be tasks? As far as the hash table is concerned, it doesn't matter. It could be anything. Okay, it doesn't have to be files. Okay, there are examples where peer-to-peer systems have been used to build directory services. Okay, there has been at least an implementation that says, can we take DNS, which is the domain name system, and build it as a peer-to-peer system. What DNS does is you give a machine name, it maps it to an IP address. Key is the machine name, right? www.umass.edu. Value is the IP address. Okay, so you can actually use a system like this to build any kind of lookup. It doesn't have to be content. Okay. Okay, so let's move on, and I'm going to spend maybe 5 or so minutes. We'll talk about a whole other slew of peer-to-peer systems that are called unstructured peer-to-peer network. What I showed you for CORD and CAN are referred to as structured system because it's a structured address space. There's a way by which you join and leave that results in some sort of a topology and so on. Okay? Now, before the structured systems came along, there were many other systems where things just grew organically with no structure in mind. Okay? And so all of these fall under this notion of an unstructured peer-to-peer system. And the way these things work is the following. I'm going to draw a picture. Okay, so let's say there are some peers that are existing in a network, and then there is some topology. Okay, so these are just some peers, and these are links between the peers. The links indicate which other peer a certain peer can communicate. Okay, so you can have direct communication only to a neighbor that you have a link connected. So when a new peer joins, okay, let's say in CORD or CAN, you have to pick an ID for itself that determined where in the network you joined. Okay, that was the way you introduce structure into the network. In an unstructured network, you use a randomized algorithm to decide who you can connect to. So when the peer joins, it picks k random nodes from this network and says, I'm going to be neighbors with this k. Okay? If k is 2, you will pick 2 random nodes. Okay? It doesn't matter how you pick any 2 and say, now I am going to be a neighbor with that node and I'm going to be a neighbor with that. Okay? So now one more node has joined. Yet another node could join and do the same thing. So you'll have to pick 2 random nodes from this network and then essentially say, I'm going to pick this one, I'm going to pick that one. Okay? And so on and so forth. Okay? So you will see that there is no real network topology that's going to emerge. It's going to be some arbitrary topology where nodes are randomly connected to k neighbors, where k is a parameter of the network. You can pick k equal to 2 or 3 or some value. Okay? So these networks, as a result, peer-to-peer networks are called unstructured networks. There's no underlying network structure that you have assigned here. Okay? That's the first thing. Okay? Now, because they are unstructured, okay, the way they also answer queries is different from what happens in this peer-to-peer networks, rather structured peer-to-peer network like CORD and CAN. Okay? So in this case, most of the requests are going to be answered by what is called flooding. Okay? So if you say so let's say you ask who has file foo.mp4. Okay? That is my key. I'm looking for a value. Okay? Okay? So you are going to send it to some peer. Okay? The peer will say, I don't have it. Let me ask my neighbors. Okay? So he is going to forward the request, okay, saying, I need to know if you know who has foo.mp4. So it's going to arrive at this node and this node. Okay? These nodes will say, if they don't have it, they'll forward. Okay, saying, okay, I don't have it, I'm going to forward back, and you won't forward to the node that it came from. So you will basically keep doing this, and essentially this request is going to flood your entire network because every node is going to keep forwarding it to its neighbors. Okay? Now, to prevent the message overhead from becoming excessive, you will essentially put a max hop count on your query, which says that every time you forward it, decrement it by 1. When that hop count reaches 0, then don't forward anymore. Otherwise, there will be a very high overhead because every query might flood to millions of nodes. Because essentially you are asking every node, do you have this object, or do you know where this object is? Okay, because there's no structure unlike the previous cases. Okay? So this is called query routing by flooding, and most of these structured peer-to-peer network, unstructured rather, peer-to-peer network use randomization to decide who their neighbors are, and because the network is growing in an arbitrary fashion, you are going to route queries by flooding. Okay? So there are many different kinds of unstructured peer-to-peer network. There was Nutella, which was actually quite popular at one point, that grew in this fashion. There are many others like this. Okay? They are very different from the structured fashion, because there the queries are routed in some structured manner until they reach the node that you wanted to reach. Okay? Here you just don't know. You don't keep track of who has what. You just basically flood or broadcast the query to everyone. Yes?
Torrent's an example of
Yeah, a torrent an example of this. No, I'll talk about BitTorrent if I get to it today, otherwise next time. Because in 2 slides we'll come to torrents. Any other questions here? Yes?
Very quick question on the previous slide. How do you decide which rectangle to pick when a new node going to join?
Okay. Question is, how do you decide where to join a network, which rectangle? So the way joins are going to work is very similar to CORD. You will pick a random coordinate for yourself. Okay, you pick some XY value. That will determine where you land. So if you say 0.5, 0.5, you will land here. Okay, that means you join that rectangle by default because that is contained in that rectangle, and those responsibilities will get split accordingly.
So these points that denote the location of the node, they are the means.
Yeah, so that's just the center of the rectangle, but you will pick a random value that will decide where you join, and then you will join some rectangle. Okay, it's a randomized join. Even this is randomized, but this just says I randomly pick my neighbors. But here you will depending on your coordinate, your neighbors are chosen for you. Okay, all right. So that's an unstructured peer-to-peer network. So because this unstructured peer-to-peer network had a lot of problems with query routing, because flooding caused a lot of increase in bandwidth usage. Every request is going to 10,000 machines, and only 2 nodes actually have that information. Okay, so that wastes a lot of network resources. So one alternative that came about was this notion of super peers. Okay, rather than having a pure unstructured topology of this form, you say let the peers make groups, and then within those groups you elect a leader. Okay, and so that leader is going to be called a super peer. Okay? And the responsibility of the super peer is to answer queries on behalf of all those other peers in its group. Okay? So flooding is only going to occur within the super peers, not all the other peers. Okay? So it limits the amount of query routing that has to happen. So what is shown here is there are 4 groups of peers. Each group has chosen a leader. They are shown in the dark circle. Okay, the others are normal peers. The dark black circles are super peers. And the super peer will keep track of what is going on in its group of peers. So it knows every object that every one of these peers stores. So when a query comes, it can answer the query on behalf of everyone in its group. It doesn't have to ask. In this case, you only knew what you had. You didn't know what anyone else had. So you had to essentially flood the network and ask every peer, do you have such and such object? In this case, a super peer knows what is stored in its, if it's content, it will know what is stored in its group, and it can answer for everyone. So in this case, okay, there's also a randomized topology, but flooding of query routing via flooding is only occurring at the super peer layer, okay, which means that there is some more limited use of network resources than before. Okay? That's the first thing. The second thing is you can select your super peers such that those are nodes that have more resources. Okay? So you don't want, let's say, if you have a phone, okay, that's on a cellular network, you don't want that to become a super peer because it has battery constraints, it has, maybe it's using cellular data which may also be constrained. But if you have a machine that's sitting on gigabit Ethernet, is powered, has low load, and it needs to be part of this peer, you can pick it as a super peer because there are lots of idle resources that it can use without harming the user or application. Okay, so how to pick the super peer itself is an interesting problem among every group of nodes, and typically you want to pick the more capable ones within each group to answer for everyone in the group because they will expend more resources. Okay, they will answer more queries on behalf of everyone else. Okay. So that's an architecture that emerged because of some of the problems that were seen in unstructured peer-to-peer network. Okay. Yes.
Is the architecture within, let's say, a circle, can it be completely random, or all nodes are connected to the super?
Right. So question is the architecture in each of the circle randomized? So it is basically an unstructured network where you simply drawn a circle of some neighbors. Okay, so based on this unstructured network, you take a group of neighbors, they form a group. Okay, and then within that they will say you are our leader, and that node becomes a super peer. So the topology is no different from this. It's just that a group of neighbors just elect a super peer, then that one is going to start answering questions. Okay.
But in that case, like, will there be, like, even, like, can there be connections between two regular peers? But they
yes, there may be connection between peers, but there's definitely a direct connection between super peers as well. Super peers are not going to route queries through other peers. Okay, so if you make super peers, they will actually have connections among them. So you have to ensure that. Any other questions here? Okay, so an example of where this architecture was used was early versions of Skype. Okay, which you probably know as an application. So Skype is a peer-to-peer application. It started as a peer-to-peer application where you could make audio calls with your friends or anyone else who has a Skype account as well. Okay? And the way Skype worked was you had to track which users are logged into the network. Okay? What IP addresses they're logged in, because IP address can change depending on where you are. Okay, whether you're logged in or not, that status can also change. So all of that information was a directory of who are the active users in the Skype network, what are their IP addresses. Okay? And that was essentially tracked using a peer-to-peer network. Okay, basically, you would have super peers. Super peers would track the status of other peers in the near vicinity. And then if you log into the network, you will query the super peer network to see which of your contacts are actually logged in. Okay, that's how it will show you this person is logged in, this person is not logged in, and so on. Okay? So that was early Skype architecture. Now they have gone away from that and they essentially put a rack of servers that track all of that for you, because this creates a problem where if your PC becomes a super peer, you will see a lot of Skype traffic even though you are not making any Skype calls. Okay, so then people complain saying, why is my network load so high when I'm not doing anything? So they have gone back from that, and they store this information on traditional servers. But at one point, the directory of users and their status was actually tracked by Skype in a super peer fashion. There's actually a nice description of Skype super peer in that book, the textbook rather. You should go and read it. There's some nice, interesting aspects of how Skype used the super peer network to its advantage. Okay, so we run out of time, so I'm going to stop here. We'll continue next time.